All right, let's do the second problem on the review. So what's this about? We've got 100 gallons in a tank of water with 15 grams of dissolved salt. So, and we know there's going to be water coming in and water going out. So the initial volume is 100 gallons, and the initial mass is 15 grams. We're told that water flows in at 5 gallons per minute and has a concentration of 1 gram per 5 gallons. So water is coming in at 5 gallons a minute with a concentration of 1 gram per 5 gallons. Test 2, I'll try to have convenient numbers like this. Water flows out at 5 gallons a minute. So those two numbers, the fact that they're the same, make things simpler. It means the volume of water in the tank remains the same. The first question is to set up the differential equation for m. So dm dt, the changing mass of salt in the tank, is the in versus the out. There's stuff coming in and there's stuff going out. What's coming in? Well, we have 5 gallons a minute. What is it carrying? All right, so 5 gallons per minute times 1 gram in those 5 gallons. Well, that's going to result in 1 gram per minute being added to the mixture. What's going out? Well, there's 5 gallons per minute leaving. The concentration of the tank is changing. It's however much stuff you have divided by the 100 gallons of water. This is changing. Initially, it's 15. When the problem starts, you've got 15 over 100 going out, but you've also got 1 gram per minute being added. How does all that work together? Well, we don't know. Let's look at this, and this will lead us to the answer. So this is dm dt equals 1 minus m over 20. That's our differential equation. Oh, and with our initial condition of 15 grams. So that's A. This is what you'd want to have for A. Now, what's nice about this is there's no explicit dependence on time, so we can actually solve this by graphing it. Let's graph dm versus dt versus m. If you're having a lot of trouble with this, it's basically because you spent too much time graphing y versus x. But you can think of this as your output, y, and you can think of this as your input, x. If I asked everyone in the class to graph y equals 1 minus x over 20, I have no concerns. I'm sure everyone can graph a line that has a y-intercept of 1 and a slope of minus 20. Where does it cross the horizontal axis? It crosses at 20 grams. It's the same thing here. We're just graphing dm dt, the output, versus m. It's an equation. It's linear in m. That's the case. What's nice about this is it tells us that 20 is our limiting value. So eventually, as t goes to infinity, m should go to 20. That's good to know. Notice that this is a stable equilibrium. If you're between 0 and 20, your derivative is positive. We're at 15, which is maybe about here. So starting with 15 grams, we're going to have a positive derivative. We're going to build up material until we hit 20. Why does 20 matter? Well, think of it. When it's 20 grams per 100, that's 1 and 5. 1 and 5 come in, 1 and 5 go out. It's perfectly balanced. All right, so this means I should be expecting solutions that are exponential in nature. This is what we expect exponential solutions to do. You start out, say, steep and you level off, or if you start closer to 20, not as steep and level off. If for some reason you had more, it would just be a reflection. So this is exponential growth that has been shifted So it's not going to 0, but it's going to 20 grams. So now actually I know what to expect from my solution. This is great. Now I'll move on to C, solving the initial value problem. And I know what my answer ought to do. This is going to be very helpful if I make a mistake. dm dt equals 1 minus m over 20. Let's rewrite that to look like the kinds of questions that we've seen in 1.9. There it is. This is the inhomogeneous term. So the first thing we have to do is solve the homogeneous equation, which is dm dt plus m over 20 equals 0. Well, that should look like exponential decay with a rate of negative 1 over 20. So you can either solve that by separation of variables, or again, just notice, and this equation comes up a lot, so it's some number e to the minus t over 20. So that's the homogeneous solution. B, we use that as a stepping stone to say, well, maybe the solution to the full equation, to the inhomogeneous equation, is a function. Maybe a is actually a function, not just a constant. And then we plug it into the equation and see what happens. So we'll get an a prime e to the minus t over 20, minus a 1 over 20 a e to the minus t over 20. I forgot to say, but hopefully you're pausing this video and working through the steps. Don't just watch me. See if you can anticipate. Pause, play, and so on. So this is m prime, and then we have plus 1 over 20 a e to the minus t over 20. This is m equals 1. So this is going to give us a condition on a. All right. Just pick up from there. So let's see, things cancel, these things cancel. So we have a prime e to the minus t over 20 equals 1. So we have a prime equals e to the t over 20. So if you integrate that or find the antiderivative, e is 20 e to the t over 20 plus c. This is where I made the mistake in class writing the solutions. I had initially written a 1 over 20 here, which I caught because I knew what the answer ought to be, qualitatively anyway. All right, so that's a. That means I go back here. I had supposed that m was the product of a and this decaying exponential. So then my solution should be 20 e to the t over 20 plus c e to the minus t over 20. Simplify, that's 20 plus c e to the minus t over 20. This looks good. As t goes to infinity, I go to 20, which I know to be my stable equilibrium. So that's good. Do my initial condition. M at 0 is 15 grams, which is 20 plus c. Right, this is 1 when t is 0. So c is minus 5. So my full solution, my particular solution to the inhomogeneous equation is 20 minus 5 e to the minus t over 20. And I've kind of talked about the limit several times during this video. Again, we can see here explicitly that the limit as t goes to infinity of m of t, the decaying exponential becomes smaller and smaller and smaller. We're approaching 20. Makes perfect sense. Also, back in part B, where we sketched our flow in a line, we can see what would happen for different values of m. They would flow towards 20. That's reflected in sketching the solutions. So everything's consistent with 20 grams. And also physically, again, thinking about if you have 20 grams in the tank, then every moment 20 over 100 is 1 per 5. Every moment 1 per 5, that's 5 gallons, 1 gram leaves the tank as 1 gram enters. So you have a constant stream of 1 gram per minute coming in, 1 gram per minute going out. 20 makes sense in 3 different ways. Physically, qualitatively through the flow in the line, and then explicitly through the solution. And all right, I'll do a video for E and F afterwards.